Okay students, in the previous session we have discussed about the PN junction diode and as well as the depletion layer, all the forward bias, reverse bias conditions, right? So in this session we will discuss about the applications of. So okay, fine, what happens if we have the flow of the current through the diode, or if we have a regulated flow of the current, which is nothing but a minimum amount of current due to the minority charge carriers, all that, right? So in this session here we'll discuss about the applications of the PN junction diode, and out of that the first one is the rectifiers, and that too in the rectifier we are going to discuss about the half wave rectifier. Half wave rectifier, the name itself speaks about that, only half of the wave. And let's understand what do you mean by a rectifier first of all. So when we have a diode and how we can use that diode in the case of or in the process of rectification, let's understand that. So the process of converting an alternating current into a direct current is called rectification. So alternating current, which is AC to DC, is nothing but the process is called rectification, and the device used for the process is called rectifier. So the PN junction diode offers low resistance in forward bias and high resistance in reverse bias. Keeping that in note, now we are going to use the PN junction diode as a half wave rectifier. Are we getting the point here? So first of all, look here, we have a schematic diagram for that. So this is a step down transformer. This is a step down transformer, and here is a diode, and this is the load resistance, and the left hand side ones, these are the input signals while these are the output signals. Are we clear with this? Okay, now let's understand how we can have the input, of course how we can have an output with respect to the input what we have given. Let's understand this. So using a single diode we can construct a half wave rectifier, you can notice here. Okay, a half wave rectifier rectifies only one half cycle of the AC input. What kind of input it is? Notice here, it will be clear for you if you understand. This is for the positive half cycle, negative half cycle. So for a complete cycle you can look at here the third figure. Look here, complete cycle, what kind of input it is? Alternating rate. So a half wave rectifier rectifies only one half cycle of the AC input, and an AC source along with a step down transformer, you can notice here, step down transformer is connected to a load resistance through this PN junction diode. Okay, the potential at the point here you can notice here it will be of having a high potential, here it will be obviously, isn't it or not? And if you consider this to be a 0 and the potential at point this point, let me give some naming so that no confusion at all for you, why to call this point that point and all. So let's call this to be A, B, and I say this point like can I call it as C? No confusion, no C representation, right? Okay, C, and okay, leave it, because if I had called D, anyway no use at all. Here again we have a diode, so that was, are we clear with this? So now at point A, B, and anyway through C it is needed, anyway that was enough, no confusion with the diode D. So now look, understand this, the potential at point A, is taken to be 0 if the potential at point B varies with time. That obviously, because we are applying the voltage the AC signal, right, and that I am calling it as V equal to V naught sine of omega t plus phi, and this is the AC input that which I am giving actually. Are we clear with this? So the potential at point B varies with time like this, and during the positive half cycle V will be greater than 0, positive half cycle, right? So V will be greater than 0 obviously, and B is at a higher potential than A. B is at higher potential than A. Suppose at any point you have to start it, so I am considering A is at a 0 potential, thus obviously B is at a higher potential than A. Now in this case the junction is forward biased because B end is connected to the diode positive end and B is at the high potential, isn't it or not? And while through the resistor A is at low potential, what kind of or what sort of connection is this? Forward bias. So now the diode is in forward bias condition and current pass through the load resistance in the direction C to A like this. isn't it or not? It conducts in the forward bias condition. Okay, right. Now the negative half cycle. During the negative half cycle, I am speaking about this condition. This just now we have spoke about this positive, negative. That's what, right, we are calling. Now in the negative half cycle, the situation will be reversed. Look at the second figure. The terminal B becomes negative while terminal A becomes positive. Situation got reversed. What happens in that situation? Diode is now in reverse bias condition. Will there be any current flow in the reverse bias condition? Obviously no. That was the reason why we don't have an output. So when we give a complete signal like this, you can have an alternating pulse. What do you mean by this? What do you mean by this? Having the same magnitude. So an alternating current we have, but we are having only current flow through in one direction, and what we call these discontinuous pulses are nothing but DC. That's it, right? Direct current, constant magnitude of the value. Are we clear with this? The current flows through the diode during positive half cycles only here, and current flows through the RL only in one direction. You can notice here, only through the positive half cycles alone, isn't it or not? Hence, what we can say this, a half wave rectifier gives discontinuous pulses, DC pulses, which you can notice here, only one direction, right? There is no other direction. That's why I am calling directly it as DC. The number of DC pulses per second is equal to the frequency of AC applied. Number of DC pulses per second is equal to the frequency of AC what we have applied here. Number of DC pulses refers to this is pulse 1 and this is pulse 2. Clear? Right. Now let's look about the efficiency of this. Efficiency of a rectifier is the ratio of DC power output by AC power input. We can write down with like eta, efficiency eta, which you can write it as DC power output divided by, that's it, right? We are getting direct current and the input is AC power input. This is what it is. So power DC by power AC. And now for a half wave rectifier, we can give eta to be like 0.406 RL load resistance divided by RF plus RL. You don't have this derivation part, just remember this equation where RF is nothing but diode forward resistance. This is diode forward in the forward bias condition, which is nothing but diode forward resistance, while RL is nothing but load resistance. We have seen the diagram, right? That's what I'm speaking about. So load resistance, and in a half wave rectifier, maximum of 40.6%, maximum of 40.6% of AC power is converted to DC. AC power converts to DC. 40.6%. Remember this, very useful for your 1 mark questions. Maximum of 40.6%, you can notice here. So eta is 40.6% of AC power will be converted into DC. Are we clear with this regarding the efficiency and all also? Okay ma? Right. Now let's look about the full wave rectifier. Just now we have seen about the half wave, right? So only one particular cycle is being used there, and with one single diode we have seen the output was like a discontinuous. But if I want a continuous, and at the same time if I want the full wave rectification, the entire wave has to be rectified, then I have to use this full wave rectifier. You can notice here in both the cycles we are actually going to have the output, and in general note, this is what the result. When we give out an AC, this is what diode D1 D2 D1 D2 D1 D2 alternate results are this. Okay, right. Now let's understand this in a proper notation. A full wave rectifier is nothing but which rectifies both halves of the AC input, and it is called as full wave rectifier. A full wave rectification can be achieved by using two diodes. You can see here two diodes, and the circuit has two diodes D1 and D2. You can see here along with a transformer, and remember we call this transformer as center tap transformer. Center tap transformer. Are you getting the point here? This is somewhat different, not like the previous kind what you have seen. This is called center tap transformer. Later again I'll draw the circuit so that it will be, if you want you can see here itself, no problem in this. Okay, right. Now coming to the point, the center tap transformer duty is in the secondary, the coil whatever you are actually watching, the secondary is wound into two equal parts. Voltage at point A, which is nothing but here it is, or you can call, oh here I already mentioned AB. Let's say suppose this one, lower potential and upper potential, here you can call it as AB here. Okay, and here it is. So here again AB is across the load resistor, you can get that. So here it is. So if one particular point is at high potential, the duty is, as it has been divided into two parts, right? The secondary coil is, so the secondary will be maintained in the second part of the secondary will be maintained in such a way that if one is at high potential, the other will be at low potential. Look at it in the second case, if this is at low potential, this is at high potential. That is what the duty of a center tap transformer, which means at any instant whatever it is, if one is at positive or the high potential, at the same instant the other point will be at low potential or the negative, which is nothing but for vice versa situation. Then what happens? Both the diodes will be in a conducting phase. Look here, diode D1, this is in forward bias situation. Because of the center tap transformer, part and part of this particular circuit has been divided, isn't it or not? So now what we can say, the positive terminal is connected to the positive here, is it or not? Hence forward bias. What happens when we have such a kind of, obviously this gives us a forward biasing current, so maximum it will be. But at this point, as this is at low potential, look here in the first figure, reverse bias, so no current will flow through the D2. That's why I have mentioned here, only through the D1 there is a current flow during the positive half cycle. While in the next half cycle, this is during the positive half cycle, during the negative half cycle, look here, now what happens, now the polarity will be shifted, will be quite opposite here. Now this point will become negative while this point will become positive. What happens now? Diode D1 is in now reverse bias situation, isn't it or not? While diode D2 is in forward bias condition, and obviously now diode D2 will conduct while diode D1 is in off situation. Now no current flow through D1. Notice here, I have mentioned here already. Now in the negative half cycle also we got the power. Thus when we give, this is division of the half cycles. So when we completely give the input, you can notice here, during the positive half cycles D1 will give the input, while during the negative half cycles, look here, D2. So at a time you can write down this loop like an alternate, like if this is because of 1, if this is because of 2, 1, 2, like that. So it will be like an alternate kind of. But notice here, all the pulses are continuous. It is not like in the previous case. In the previous we got a discontinuity, while here we don't have. So a constant of, and the same magnitude, and that too in the same direction. What we call, the magnitude is in same direction and does not varying with time. What we call that kind of current? DC current, isn't it or not? And have we converted this AC to DC? So that is what here. Now one more point is the number of DC pulses per second. Number of DC pulses per second of the output, whatever we are actually seeing here, is equal to twice the frequency of AC input. Twice the frequency of AC input. So while in the previous they are equal, while here in the full wave rectifier they are double. Coming to the efficiency, just like the previous, here also we can give efficiency eta can be given as DC power output, DC power output by AC power input. That's it, right? We can write down, and for this it will be nearly 0.812 RL divided by RF plus RL. You can write it as the same symbolic representation. Capital RL is nothing but load resistor, RF is nothing but forward bias resistance. And now you can write down this to be like 81.2% of AC power will be converted to the DC. 81.2% of AC will be converted to DC. Now are we clear with this? Again I am telling you, remember these values are very very important things for you. Are we clear with this, ma? Okay, right. Now let us see about a special purpose of a PN junction diode, which is nothing but Zener diode. You can see here, it's called Zener diode. The circuit symbol is here, you can notice Z like, so Zener. The difference between the PN junction diode and Zener diode, hope you understand this. Okay, and even in the circuit also we can identify which is a PN junction diode and which is a Zener diode also. In the laboratory we can notice that you have the experiments, so there we can notice. And let's look about this Zener diode, and let's understand and the various similarity and as well as the difference with respect to the PN junction diode. Okay, the properly doped PN junction diode which has sharp breakdown voltage when operated in the reverse bias condition is called Zener diode. So a properly doped PN junction diode which has sharp breakdown voltage, you can notice there it is VZ. Sharp breakdown voltage when operated in the reverse bias condition is called Zener diode. Are we clear with this? Heavily doped PN junction diode, simply to say, is nothing but the Zener. Okay, and for a heavily doped diode, the depletion layer is very narrow, obviously will be very small. And when the reverse bias voltage across the diode is increased, intense electric field set up across the depletion layer breaks the covalent bonds in it and thus produces a large number of electron hole pairs, resulting in a sharp increase in the reverse current. Regarding this, we have already studied under the topic called Zener breakdown. Same situation here also. So when large amount of voltage is applied and in a very short range, that as it is heavily doped, a very strong electric field will be applied and that disrupts the bond, and thus we can have a very short range of the in a very small amount there will be a breakage of that particular diode over that, and you can notice the sharp increase in the current here itself. In the graph you can notice the second part. The first part is very quite similar to the, in the case of forward bias it is in the just like to the PN junction diode. Look here, this is what the sharp increasing in. Are we clear with this? Now because of this particular property, it can be used, that means the Zener diode can be used as a voltage regulator, like also we can also use it like a voltage regulator. So first of all let us understand this VI characteristics, nothing but voltage versus current characteristics, so that we can see this regarding clearly. Okay, the voltage current characteristics of Zener diode I am speaking about. You can notice here the figure is very quite similar to the PN junction diode. Okay, so first of all let's start from the forward bias condition, which is in this first quadrant. So in the forward bias, its characteristics are quite similar to that of ordinary PN junction diode, isn't or not? And when reverse bias, look here in the reverse bias, third quadrant, and when reverse bias, a small reverse saturation current will flow through it, and which remains approximately constant until a certain critical voltage, and that voltage is called breakdown voltage, and until it reaches there we can call that critical voltage, and it's called breakdown voltage also. The current value is almost constant, you can notice there, and from there it has been increased very sharply, which means at this voltage, breakdown voltage, the reverse current increases. Here it is, the reverse current increases, isn't or not, sharply to a particular high value. This breakdown voltage is called Zener voltage, or the reverse, and the current is nothing but, and the reverse current is called Zener current. The Zener voltage depends on the amount of doping, and a heavily doped diode has a narrow depletion layer and consequently a lower breakdown of Zener voltage, or you can call it as a Zener voltage. But if the diode is very lightly doped, the breakdown of the junction will occur at high voltage, and that was having a high values. Are we clear with this? So depending upon the doping we can have this particular breakdown values. Regarding this we have already discussed in avalanche and all. So basing on the doping alone we can have heavily doped refers to that was, and when we heavily doped and operate in reverse gives us the Zener diode. Are you getting the point here, ma? Clear for us, right? And the circuit symbol also I have mentioned here, which is nothing but, okay, right. Thank you.